let's look at Gibbs free energy and spontaneity again. So this is the change in Gibbs free energy, and we know that for a reaction to be spontaneous, it needs to be negative. So I'm going to write that here. It's spontaneous. And if that's true, that this, we say the forward reaction is spontaneous, and I'm writing that by that arrow, then if I consider the reverse reaction, it would be non-spontaneous. Basically, that's saying that the products are favored here, and so the reverse reaction, of course, would have a positive delta G. Okay. What if the change in Gibbs free energy is near zero? If that happens, it means that neither reactants nor products are particularly favored over the other, and we have what we call an equilibrium reaction. And so we give you a range for that. It's not just at perfectly zero. It's when you're close to delta G, you can have an equilibrium reaction going on. If it's, toward the negative side, then the products will be slightly favored, but still equilibrium. If it's toward the positive side, then the reactants will be slightly favored, but still at equilibrium. Remember, this means equilibrium reaction means we have a reversible reaction. We use the two arrows. And equilibrium is when those reaction rates are occurring or have the same rate, forward and reverse. Okay, so if delta G is less than, this will be kind of our guideline, -10, then the reaction is spontaneous, going to the right. So sometimes in a reversible reaction or in these situations, we refer to the forward reaction and the reverse reaction. If we don't say which direction is spontaneous, forward or reverse, then it's assumed that we're talking about the forward reaction, the way that it's written. But we may say, in this case, like if it's positive, we may say that it's spontaneous, but we would say to the left. Okay. And in this case, we would say that the reaction reacts, in other words, to the left would mean that it does react this way. This is just a little preview to our next lesson on equilibrium. And basically, we will see that Gibbs free energy is involved with a constant, K. This is the thermodynamic constant. And what K does is it compares how much is in the products to the reactants. In other words, when this reaction is at equilibrium, is most of the material in the product form, or is most of the product in the reactant form, or is it 50-50? That ratio is K, and K is related directly to Gibbs free energy. And we'll be learning about Kc as a constant for equilibrium, and we'll discover that this K is actually the same thing as the one determined from Gibbs free energy. And just a little bit more about equilibrium and Gibbs free energy. You have an equilibrium mixture when these two, the reactants and products, are similar Gibbs free energy. Remember, we said 10 was our guideline, plus or minus 10 kilojoules per mole. And if you're in that range, sometimes the minimum, the lowest, is when you have a mixture of reactants. So if this is all reactants and this is all products, in this case, the lowest most point, the most stable Gibbs free energy, is in between. So in this one, I would say it looks like there's probably more product than reactant at equilibrium.